So as I was mentioning in the beginning, in 8.2, we focus on sequences. And then in 8.3, we'll focus on series. We've reviewed both of those and tried to get an idea of what they're about, what we're talking about, and the notation and such. But now we're going to dive in a little bit more aggressively and talk about certain kinds of sequences, certain kinds of series. We're going to have some formulas for calculations and things like that. So 8.2 begins with Theorem 8.1. And this is on page 607. So it's an idea theory, and it talks about trying to evaluate the limit of a sequence. So say I'm going to just write it more loosely with my own language than trying to copy exactly what they have in the book, but it'll be pretty close. Say we have a sequence of a sub n's. And we have a function f of x. So then if f of n is equal to a sub n for all natural numbers n, meaning that when you plug a whole number into the function, what you get is the appropriate nth term of the sequence. Then if the limit as x goes to infinity of f of x equals L, then the limit as n goes to infinity of a sub n is also equal to L. So what is this all trying to get at? It's basically trying to say that when you are trying to evaluate the limit of a sequence, when you're trying to figure this thing out, and you have a formula for a sub n, for the nth term of the sequence A, well, you can consider that formula as if it was a continuous function of x. And then if you could evaluate that continuous function from stuff that we used back in chapter 2 and get an answer, then that answer will be valid as the value for the limit of the sequence. So it's basically saying you can take the limit as you normally would, as long as there's some function that matches up with the sequence. So I tried to give an example before where if you try to have like a power on a negative number, we have no such function for that. We don't have a function that we can use for that. So as an example where we couldn't use this theorem, if you had a sequence that involved a power, nth power on a -1 or something like that, then you're not going to have an f that you can use to evaluate that limit. You're going to have to do something else. But in the case, in otherwise, you can do that. So for example, and they do an example before this. Oops, let's change that to black. For example, if you have a sub n is equal to, and the formula that they give you is like 1 over n squared plus 1. So this is a sequence. So then you could try to determine the limit as n tends to infinity of a sub n. So your natural tendency is want to take the limit as n tends to infinity of 1 over n squared plus n, the formula that you have for a sub n. Well, basically, what this theorem says is that you can do that. Because when we did limits in chapter 2 of this type, when we considered things like this in chapter 2, we weren't looking at functions where you could only plug in whole numbers. And all of our limit laws and limit properties, they only applied to things like that. So now that we have a limit with whole number values n, or natural numbers n, 1, 2, 3, 4, 5, the question is, can we still sort of take the limit of that expression like we did when it was 1 over x squared plus 1 instead of 1 over n squared plus 1?
Quick question.
Yes.
What's the symbol you used? And suppose fn equals an something upside down an?
So yes, so this symbol here means for all. Thank you for asking to help clarify that. Yeah, so the upside down a means for all n. That goes back to usually the notation used for like epsilon delta proofs and crap like that, which nobody remembers. Is that okay?
Yeah, that's fine.
That's what you're asking about, right? Yeah.
Okay. Yeah.
Okay, so then we're still stuck in the same position we were just discussing of trying to remember how to evaluate our limits from chapter 2. And because you're going to infinity, you can't really just plug in an infinity and do the arithmetic, even though sometimes you can think of it simply in your mind that, maybe you're thinking here that this is like 1 over infinity so that you would get a 0. But we have to draw back on that understanding and be careful because, as I pointed out earlier, you can't really do arithmetic with infinity. You can visualize it that way, and sometimes that will still lead you to the correct answer, but you have to be careful about that. And the main thing is that, infinity plus infinity, infinity divided by infinity, as soon as you have more than one infinity, it's a problem. And that usually you have an indeterminate form and you have to explore it more deeply. But other than that, we can approach these with a limiting approach that we normally would have used in chapter 2, as long as the function that we're working with is something that we could have worked with in chapter 2. That's basically what theorem 8.1 is saying. Now, they don't give any examples after 8.1. I just pulled this one out of there just to talk about it. They instead immediately move to theorem 8.2. And again, also from chapter 2, you may or may not recall there were these things called limit laws. And now we have limit laws for sequences. Still on the same page. So what were the limit laws? Because then we can sort of analogously transfer them to what we're going to look at here. The limit laws talked about taking the limit of functions and what you could do when you had a more complex function. So sort of reminder. From chapter 2, we had stuff like the limit of f plus g is equal to the limit of f plus the limit of g. And we had the same thing for f minus g, f times g, and f divided by g. And so the limit laws could be read as like the limit of a sum is the sum of the limits, the limit of the difference is the difference of the limits, the limit of the product, the limit of the quotient, etc. And these had little caveats about the functions being sort of having a value, and this was usually the limit as x went to some value a instead of going to infinity or something like that. So these things were called the limit laws. So the limit laws for sequences will be trying to evaluate the limit of a sequence which is created by a sum of terms, being the limit of the sums of those sequences. So already it's going to be verbally challenging. So let's look at the first one and see what it says and see if we can imagine how they're translating over limit laws to our new sequences. So it says that you assume you have an A sub n, B sub n, that have limits A and B. So what does that mean? The limit as n goes to infinity of A sub n is capital A, and the limit as n goes to infinity of B sub n is capital B. So that you have two sequences in and of themselves where you can see the limiting result of their terms. So limit law number one says that the limit as n tends to infinity of the sequence that you would get by adding A sub n to B sub n. So if the terms of a sequence can be viewed as being the sums of terms of two individual sequences, and you want the limit of that sequence of sums of sequences, you get the sum of the individual sequences limits, which in this case is A plus B. Much harder to say than to write the symbols, but harder to keep straight what's being discussed here. So this can be read as the limit of a sequence of some terms is the sum of the limits of the individual sequences terms. Questions, comments, discussions about what that's trying to say? So we can think of a silly example just to put some numbers on this because there's too many letters and words to juggle this. So imagine that the sequence of the A's is 2.9, 2.99, 2.999, etc. And the sequence of the B's is 5.1, 5.01, 5.001, 5.001, etc. So I've made a super simple example because if you add each of these up, you get 8. So what this would really be is the limit as n goes to infinity of this constant sequence 8. So, but what you can see is that the limit of the A's would be 3, and the limit of the B's would be 5, and therefore the limit of the total would be 3 plus 5, or 8. Questions, comments, discussion? Okay. Pretty good. Okay, so then actually you could do the exact same thing if this was the difference as well. So you can put an A and B with a plus or minus here. So then the second limit law translation for sequences is that if you had the limit as n tends to infinity, where the sequence that you got, all the terms were a constant multiple of some other sequences terms. Whoops. So if I had a limit as n went to infinity of some constant times A sub n's, and I already knew that the limit of the A sub n's was capital A, then I can pull that constant outside of the limit and say that this is C times A. So in terms of sequences, number 2 says the limit of a constant times a sequence is the constant times the limit of the sequence. And 3 and 4 follow along to finish off this theorem with the limit of a product sequence and the limit of a quotient sequence. In the case of the product, you would get the product of the sequence's limits, and in the case of the quotient, you would get the quotient of the sequence's limits, provided that b is not equal to 0, because you can't divide by 0. So this gives you an ability basically to manipulate in the same way you used to do, use limit laws for functions when you're taking limits of sequences. So for the last few minutes, let's try a simple example. They have example 1, A, B, and C. If you look at B and C, you need to use L'Hopital's rule for more challenging limits like you did back in chapter 4, which you may or may not remember how to do. Let's take a look at 3 instead. And then I would suggest that you try to continue our work after we're done here today by looking at some more challenging examples that are in the same one. So we have example 1, and parts A, B, and C are on page 608. But we'll just take a look with our last 5 minutes at A. And it's similar to something we've already looked at, but it's just a reminder. So it says, determine the limits of the following sequences. And so for A, the sequence is 3n cubed divided by n cubed plus 1. So we're supposed to determine the limit as n tends to infinity of a sub n. So again, it puts us back in a position where we're evaluating limits similar to we did in first semester calc. We do have to keep in mind that we're going to treat this like a function, even though it's not a continuous function. It's just involving natural numbers n. So we've done one like this already, in which I simplified it algebraically. But let's talk about what the last 2 theorems allow us to say here. So theorem 8.1 basically said I can consider this thing here and say, well, if this was a function of x and I plugged in values of n, could I evaluate that limit? And in this case, we could, and therefore we could do it exactly like we would have done it with that kind of a problem in chapter 2. Now, the other possibility is in 8.2, we could use limit laws to try to simplify or work with this a little bit. For example, I could say that this is equal to 3 times the limit as n goes to infinity of n cubed over n cubed plus 1. All I did there was I pulled the constant 3 outside of the limit, and that would be using the limit law for sequences in part 2 that we just looked at. So that's what the theorems are saying. It's not going to allow us to do anything different or than we've done in the past. They're just formalizing certain things that you can apply to sequences like you would have if you were working in chapter 2 and working with functions, and that we can do that from time to time. So does somebody want to offer up a suggestion of what you think you would get for this limit?
I did it a little bit differently and just multiplying the top and the bottom by the highest power. Could I have done that, or is that not quite right?
That's fine. And let me sort of show how that supports with the new work, because the new work confuses you about like, what am I supposed to do? What am I not supposed to do? So what you would say is the work that you just described was how we dealt with this when it was just a normal function. So if you had, f of x equals 3x cubed over x cubed plus 1, that's exactly what you would have done, right? You would have sort of basically said, I'm going to multiply the top by 1 over x cubed. Whoops, I said x. Right? In order to get rid of that highest power, and I'm going to do the same thing on the bottom, right? And then this would have led you to 3 over 1 plus 1 over x cubed. And then when you take the limit as x tends to infinity, this part goes to 0, and then you get a 3.
Right, and then so that's theorem 8.1 says I can do that, right?
Theorem 8.1 is trying to say that work that you did back then, you can also apply here.
Right, okay.
And it is a different situation because this is a sequence, it's not a function, but all of that work is still valuable and applicable, and that's the theorem is just trying to open up the floodgates and say, yeah, go ahead and do that when it makes sense. Is that okay?
Yes, yeah, that makes sense.
Right here, we basically divided each term by the highest power, which was x cubed in this case, right?
Exactly. So that was a strategy that actually even comes from pre-calculus about sort of trying to determine the end behavior of a rational function. And that basically you can divide out the top and the bottom polynomials by the leading highest power and see what's left in order to evaluate.
Got it. And we can do that whenever we have a limit that's approaching infinity.
Well, the thing is that what you have is a fraction where the top and the bottom were both approaching infinity and they were both polynomials. Then it makes sense. The other comparative tool, which could also be used, again, that applies to functions, not to sequences, but 8.1 allows us to do that, is because this was of the form of an infinity divided by infinity, you could use L'Hopital's rule. You could start differentiating the top and the bottom until, you end up getting a 3 after you do that 3 times, basically.
So in the sense of the rules that we just learned above, could we use number 4, which is the limit of A over the limit of B?
Great suggestion. So that depends on them having limits, A and B.
Oh, I see. Okay, right.
And what you'd find is if you tried to take the limits of the top and the bottom separately, they would both be infinities, and those are not A and B numbers. So they would say that those don't have a limit, they diverge, and therefore we couldn't apply number 4. So number 4 of the limit laws will only apply if those numerator and denominators actually have values for their limits. Then you can substitute those values, assuming the denominator value is not 0.
Okay, cool. That makes sense. Yeah.
Okay, well, I'm finishing there, and that's the exact same place I got to with my morning class, so we can stop on the same page, basically. And we're 1 page into 8.2. Definitely 8.1 is a big challenge because it kind of does a lot in a short period of time. Just sort of assumes that you hopefully might have seen that before, but does explain it from scratch. So if it's very overwhelming and challenging, it means you're probably going to want to spend more time getting accustomed again to the notation in this chapter. If some of this stuff came back kind of more comfortably, that's great. Then you can move on to other sections more quickly. We'll need to move on probably a little bit more aggressively than we did, but for a first day, I think we did great today, and I appreciate you guys for all coming. So we'll finish there, but I'll just take any last minute questions if anybody has any.
Yeah, so the limit of this current problem is 3.
Correct.
Okay.
From either L'Hopital's rule or from that algebraic manipulation or any of those things.
Cool.
Other questions? Okay, so our goal is to do the best that we can with this somewhat challenging and limited format and get used to the software, get used to what we can do and what we can't do, and try to help you guys keep going through the material so that hopefully when we eventually come back, we haven't fallen so far behind that we can't complete the class, and that we can focus on midterms maybe after we get back. But in the meantime, I will have an office hour as usual online in this same format tomorrow morning at 10 a.m. if you want to come in with questions. And then we'll have another session like this on Wednesday, same bat time, same bat channel. Any questions at all before we finish up?
It's an awesome reference. Thank you.
Thanks. All right, guys, I hope to see you soon, and I'll see if I can figure out how to get videos of these posted somewhere.